Today I'm going to show you a chemistry problem-solving method that we're going to use for the next few chapters. So pay close attention and feel free to pause this video or watch it again if you need to. I'm going to work through 3 problems to show you how to use this problem-solving method. So first of all, notice that they're giving us a reaction. We're mixing hydrogen and fluorine gases to make hydrogen fluoride. They're giving us the equilibrium constant. That means it's K. That right there is K. And they're giving us basically the moles and the liters, which means we can get the concentrations from that. And it says to calculate the concentration of each thing once it has reached equilibrium. So first thing is, let's go ahead and write out a reaction so we can see what it looks like. We have H2 gas, and we're mixing it with fluorine gas. So here's what our reaction looks like. We also can write out K because it gives us K in the question. And we know that based on that reaction, K is equal to the products. In this case, our product is HF. And we're going to raise that to the second power because of that coefficient 2. And then over the reactants. And these don't have coefficients, so they won't have any exponents. All right, the next thing we need to know before we can set up our icebox is we need to know which way the reaction is shifting. And there are 2 ways that you can decide which way a reaction is shifting from an equilibrium question. One is if you know that you have 0 amount of any of the reactants or products, the reaction is going to shift towards the 0. So if you have 0 amounts of product, it will shift towards the products. 0 reactant will shift towards the reactants. In this case, we don't have 0 of anything because it says you have 3 moles of each component. So if you're given amounts of all of your reactants and products, what you have to do is to calculate Q. And from our last video, you should have seen that Q is the same thing as K in terms of the math, but it's you're calculating it when it hasn't yet reached equilibrium. And so this question says in a particular experiment, you have 3 moles of each component in a 1.5 liter flask. It does not say that those are the amounts at equilibrium. In fact, that's the whole point of the question, is that you're trying to solve for the amounts once it's reached equilibrium. So that's kind of your clue that these are not the equilibrium amounts. So we're going to go ahead and set up Q the same way we set up K. So we have the concentration of HF squared over the concentration of hydrogen times the concentration of fluorine. And we can go ahead and set these up, but notice that brackets means concentration, and that means moles per liter. So for each one of these, we had 3 moles in a 1.5 liter flask, which means each of these are at 2 for the molarity. So we're going to use 2 for our molarity for our concentration. So we plug it in for each component. 2 squared is 4, and 2 times 2 is also 4, and 4 over 4 is 1. So now we know that Q is equal to 1. So now what we're going to do is to compare our Q value to our K value, because this will tell us which way it's going to shift. Q is less than K, so 1.15 times 10 squared is 115, which is way bigger than the 1 of the Q. So when Q is less than K, that means products are favored. So the reaction is going to shift towards the products. And now that we know which way the reaction is shifting, we're ready to set up our icebox. And ICE stands for your initial amount, delta stands for the change, and then the amount at equilibrium. So we're going to start with a certain amount of our chemicals. We have, in this case, 2 molar of all 3 of those things. Then something is going to happen. So the reaction is going to shift in one direction, means it's going to go faster in one way than the other, until it reaches equilibrium. And then once that change has happened, then it has reached equilibrium. Notice that these are going to be, they can be in units of moles or concentration, depending on the question. So in this case, we're going to use concentration, but in some of the later chapters, it'll make more sense to use moles, and I'll show you that when we get there. So let's go ahead and rewrite our reaction. And we can go ahead and plug in these amounts. So initially we had 2 for our molarity here. We had 2 for our molarity here and 2 here. We know that the reaction is going to shift to the right, which means it's going faster in the right direction, which means we're going to increase the amount of products. So let's put a plus sign here, and we're going to decrease the amount of reactants because they're getting used up to form the product. So whichever way it's shifting, the things on that side will be the plus sign, and the things on the other side will be the minus sign. And we don't know how much it's changing yet. That's what we're trying to figure out. So we're going to plug in x here. However, x is going to change proportional to the coefficients in the reaction. So notice that H2 and F2 both have a 1, so we're going to leave that as a 1x, but 2 is in front of the HF on the product side, so this needs to be 2x. HF is going to change twice as much as fluorine and hydrogen because there are twice as many moles in the reaction. It's a mole-to-mole ratio. So when you're setting up your x's, again, you're going to put pluses on the side in the direction that the reaction is shifting and minuses in the other side. You'll plug in x's for the change amount because we don't know how much it's changing yet, and make sure that the x's have the same ratios as the coefficients in the reaction. So 1, 1, and 2 in this case. And so now we can say that at equilibrium we have 2 minus x for H2, we have 2 minus x for F2, and we have 2 plus 2x for HF. Now what we can do is to plug those amounts into our K. So we already know that K equals HF squared over H2 times F2. But these are equilibrium amounts. So now we're going to plug in what we got in our icebox. Don't forget that square. And now we have this huge algebra equation. So the first thing I want you to notice is that the bottom of that fraction is 2 minus x times itself. So what I'm going to do is to rearrange that and put those two together. Because now both the top of the fraction is squared and the bottom of the fraction is squared. So what we can do is to go ahead and square root this whole thing and square root k, don't forget to do both sides, and that will get rid of the squares. And so now we have k equals like this. And I forgot to plug in, but we know what k, the number is, so we don't need to use k anymore. We can just substitute the number. And now it becomes one big algebra problem. So what I want you to do is to go ahead and see if you can solve this math problem and see if you can calculate what x is going to be doing the algebra. And I'll work through this in class if you have trouble with the math for that. So this is going to end up being, if you can solve for x correctly, pause the video and see if you can solve for it. If you solve for x correctly, you should get 1.528. And now that we know x, once you solve for x, then you're going to plug x back into these amounts because these are equilibrium amounts, and that's what the question is asking you for. So now we can say that at equilibrium, the concentration of H2 is equal to 2.000 minus 1.528. And we can do the same for F2, and it'll actually be the same thing. And then for HF. And that's the final one. So that's the end of this question. Those are the 3 answers. And I'm going to work through 2 more problems that are similar to this. So stay tuned for the next videos.